Define monotone sequences in this video. There's two parts to this definition, I guess. So say we have some integer z, we say xn, a real sequence xn is, and then non-decreasing, if for all little n greater than, that's not greater than, greater than or equal to the big N, our integer here, if xn plus 1 is greater than or equal to xn for all n greater than or equal to n. Okay, so we say it's non-decreasing in the region where n is greater than n if for every n greater than n, xn plus 1 is greater than xn, and that essentially, if we were to plot our sequence on a graph, so we have 1, 2, 3, 4, these are our n, this is our xn, we've got some value here, like big N, on the x-axis, so the sequence can be doing all sorts of things up to that point, but then after this big N, every point in the sequence has to not get smaller. Okay, so that's what that would look like. And then similarly, non-increasing, and I shouldn't really be writing for all here, just for, so if for n greater than or equal to n, if x n plus 1 is less than or equal to xn for all n greater than or equal to n. And this graph would look similar. We've got our n here, and then after, alright, we have this non-increasing sequence, so every point is getting further and further down, or staying level at least. So if xn is non-decreasing or non-increasing, for n greater than or equal to n, then xn is monotone. Okay, so monotone, if a sequence is monotone, it just means it's either non-decreasing or non-increasing. So now we'll look at why this is useful. We've got something called the monotone sequence theorem. So there's two parts to this, as you can guess, because there's two parts to the monotone definition. So we'll let xn be non-decreasing. And just note, this is not the only reason monotone sequences are useful or interesting, just one reason, but this is all we're going to go through for now. So if the set xn's such that, this is what this little sign means, such that n's greater than or equal to n. So remember, this n greater than equal to n is where our where we're non-decreasing, so I should have put that in here. Okay, so for n greater than or equal to n, so the set of xn's beyond this integer n is bounded above then let's give this set a name, we'll call it A, is bounded above, then xn converges to what we call sup A, or the supremum of A. And if you've covered some sets, you'll know what the supremum is. The supremum of a set is the maximum element, okay, or the maximum element in a closed set, but supremum really is, it's the least upper bound, so it's the smallest number that is an upper bound for the set. So essentially what this first part A of the theorem says is, if we have a sequence that is non-decreasing and there's some bound, there's some upper bound that the set of xn's can't surpass, then the sequence converges to the supremum of A, the least upper bound, okay? And then also, if A is unbounded, xn diverges to positive infinity. Right, part B, see if you can figure out this part of the theorem. It's very similar, just for non-increasing theorems. So I encourage you to pause, maybe write this out formally in a similar form to here, and I'll go through it right now. So let xn be non-increasing for n greater than or equal to n if the set, and we'll call this set B, even though it's the same as set A, of xn such that n is greater than n, is bounded below this time, then xn converges to the infimum of A, inf A, and inf is the most lower bound, so this is the biggest number that's a lower bound for this set B, and I'll put A, but I'm supposed to put B, there we go. Right, so if B is unbounded, well, I shouldn't really be writing unbounded because it could have an upper bound, so it's not bounded above, we'll say, and again for B, is not bounded below. Then xn diverges to negative infinity. Okay, so you can see now, if we can identify that a sequence is monotone from some integer n, we can then, to see if it converges or diverges to infinity, we don't have to do some of the more complicated tests we've been doing in the last couple of videos. We can just check if the set that we've stated here, these sets A and B, depending on which case we're looking at, are bounded or unbounded, and then that tells us what we want to know about whether xn converges or diverges. That's it for this video on sequences and series. I'll see you on Sunday for another video following on from this one. If you do have any questions about this, please just let me know in the comments, and if you haven't seen the earlier parts of the series on sequences and series, I will link the playlist at the end of this video. If you did enjoy, please like and subscribe.